Good evening, everybody. Okay, my name is Felix Winkelmann. I'm working for Bevuta IT GmbH, whatever that means. And we're doing, we're using Scheme in the development of customer software. And I'm talking about Scheme implementation techniques and loads of things that are related to that. It's a bit of a wild ride, really. It covers all subjects, and it's too detailed in places, and in other places it doesn't have enough detail. So just take it as a wild ride and ask if you want, if something is going out of hand or anything, or if you have questions to specific subjects, ask after the talk. Okay? All right. So Scheme, that's the language I'm talking about. It's a dialect of Lisp, a standardized dialect. There are various standards. R5RS was the longest, or is the standard that was implemented in most systems, followed by R6RS, which wasn't accepted by the community, more or less, and R7RS is now in the works and nearly finished. R5RS was designed by consensus, so it was unanimously designed, and the advantage of that was that there were no compromises made. So you have a very clean language, and many things were left open for experimentation with the language. That gives a lot of leeway to the implementers to try out new approaches for certain language features. And this is one of the advantages, I think, of the Scheme language. It's very minimal, but it opens up lots of ways to try certain features out. Okay. Scheme, being small, is implemented on all platforms, in all languages. It's embedded as a scripting engine in many projects. There are implementations in all possible target languages. Runs as desktop applications on mobile phones, on mobile devices in general, mainframes and everything. I'm talking about specific implementations later. It's used as an embedded scripting language in games, graphics software. There's a wonderful live programming tool called Fluxus, where you program in front of an audience and have music and everything, and the 3D graphics, and it's great. Audio software uses it. I forgot the name now. Actually, it's used in spam bots too. It's probably the dynamic language that's used most because just of the distribution of the bots. It's actually used for configuration of. Well, there's one known use of configuration of spam bots, which is crazy. You can use it as a shell replacement. There is a kernel module actually evaluating Scheme code inside the kernel, and it has all sorts of uses. What are the advantages of the language itself? It's small, simple, it's very elegant, very general. You have very few basic concepts. And these concepts are usable in the most general way. So we have very few restrictions, which is kind of a challenge for implementing it, but that's the reason I'm talking about this here. And you have the basic tools, data structures and everything, very minimal, and you have a very powerful syntactic abstraction facility, commonly known as macros or syntax definitions. And these syntactic abstractions can be used to actually provide the basic blocks of using these tools. basically to create specific or domain-specific languages, and this is extremely flexible. You shape the language according to your needs, and you try not to just put together what you have. You can shape it yourself. And code is data, and data is code. Like all Lisps, it's very easy to work with code and with programs, and to transform them, optimize them, do whatever you like. Here's a list of a few major scheme implementations. This is totally subjective, of course, and I'm highly biased, and I'm just putting together a small list. Most of them should be known. There's Shea Scheme, which is a commercial scheme implementation. Extremely good, extremely well designed, very fast, very expensive. Used in government projects and other things. Bigloo is a very fast implementation, has some restrictions because it's really designed to be high performance. Racket is probably known as used in education a lot, and is a very nice development environment and all sorts of cool tools, lots of libraries. Yeah, and it's used for a course, for a curriculum, I think is a word. How to design programs, which is a book, and this is the implementation. MIT Scheme is an older scheme dialect, slowly dying out because of technical problems or just design decisions made a long time ago. Gambit is a well-known scheme implementation. It's very fast, very well designed, highly tuned. It's very good. Guile is specifically made for embedding in applications. Gauche, you say gauche? I think that's the word. That's how you pronounce it. It's a Japanese scheme implementation, also very nice, very geared towards system administration and practical things, the daily things you have to do. There's chicken. Perhaps somebody has known about it. I love talking about chicken. I wrote it, or I started it, so it's I can't say anything about chicken because I'm just too biased for that, but that's the context where I come from, scheme-like. There are other implementations too. There are loads of them, actually. This is they have crazy names. I mean, Biwa scheme, librep, six scheme. I never heard of them, but I found a list in the internet, and there are probably loads more because scheme, being a small language, is you quickly implement it, and it's just fun. And so it's sprawling. It's great. Some people think this is a problem, actually, that you have so many implementations and and everybody tries out. We have a very minimal standard and loads of implementations, and everybody does things differently, which aren't nailed down in the standard. But on the other hand, you have a broad spectrum of features and of ways to approach the problems you have to solve when implementing a language, and it's a universe of options, really, and that's pretty cool. I think it's an advantage. What's happening here? Whoop. Okay. Interesting language features of Scheme that make it interesting and both challenging is you have dynamic typing. So types of values types are attached to the values and not to the location where the value is stored. Not the variables are typed. You have garbage collection. You have tail calls. That is a call, and the last position of a function is iterative. So you can express loops using recursion, which is very elegant. You have first class continuations. I'm just going to try to explain continuations because it's very weird. It allows you to jump back in time, sort of, and have more control over the program flow, the control flow. And you have evaluation. You have runtime evaluation of code, and this is very flexible and allows you to be very dynamic. Now these are all challenges in one or the other way to implementing Scheme efficiently, but we are getting to that. Okay, now interpreters, one way to execute Scheme. The basic approach is you have S-expression tree of Lisp, the S-expressions Moritz talked about. You just walk them, evaluate the code. And that's the natural approach, really. SCM is a Scheme implementation that does that. Guile did that once. They have a bytecode interpreter now. It's very dynamic. You can execute fast. There are no translation steps or so, but it's slow. That's the problem, unless you optimize it heavily and trying to start doing tricks. But in the end, it's the natural approach to do this. This is what you want. This is John McCarthy's meta-circular interpreter. I mean, it was revolutionary, really. This is in the 50s. This was done, and this is one part of it. It's actually have eval and apply, and this is M expression notation. This was before S expressions were invented, and this is what you want. It's very, very elegant, very nice. What you get is this go-tos, if def cautious. This is nice. And this is from the SCM Scheme implementation. And it's just a mess. It's unmaintainable, really. But to get this fast, you really have to do all sorts of tricks. I mean, if you just count the number of go-tos in there, it's crazy. But you have to cut corners to get this to an acceptable speed. SCM is actually one of the fast Scheme implementations, of the interpreter-based implementations. But you see it in the code. They have tuned crazily. The next step in executing or evaluating code is by doing the bytecode interpreter, which is used in many language implementations, not only Scheme and Lisp. God, this thing here is terrible. I hate these. Guile is a bytecode system. There are many others. I think Gauche is bytecode too. It's straightforward. You just implement a custom virtual machine. It's relatively fast up to a certain limit. There's always a horizon that you can't reach, but you can come up. You can get it relatively fast, and it's easily implemented. Threaded code is one possible variant of this bytecode interpretation, where you don't have bytecodes that you fetch and do something with it and get the next code. Threaded code just takes code addresses. It's perhaps if someone knows for threaded code is the approach they use. It's faster. Petit Chez Scheme is a free variant of the Chez Scheme implementation. They use threaded code. It's very fast for an interpreter. Closure compilation. That's a new, or not that new. It's another possible way to execute code. This is an interesting approach. It's from University of Montreal. Mark Feely and Gila Palm invented it. What you do is you build up a closure tree. You take the source expressions and build up, I'm going to show an example in a moment, a tree of closures, and this gives you a very clean way of implementing a Scheme interpreter in Scheme, which is still relatively fast. It's very clean and very elegant, and you can, with a few minor things that are low level, you don't need special features. You don't need access to the basic mechanisms. It's very call intensive, so you have a certain performance limit there. But it's a nice way of writing an interpreter. So we have an example. I hope you can read it. It's very small. I try to cram as much meaning into this slide as possible. This is what you do is you compile. You compile an expression. This is expression. This is a static environment. Get to this in a moment. And you walk this expression and transform the nodes, the values, into a closure. So you have a local function here named walk. It takes an x. It takes a sub-expression. And now we look. What is this? We have various. This is just a part of the possible ways. You have a symbol which represents a variable. You have a conditional if, let, procedure call. There are more. This is just a piece, just a part of it. And what you do now is for every sub-expression you return a closure. So let's take a simple approach here. If, for example, we have 3 sub-expressions, we walk them. Each walk returns a closure, and we return another lambda, another closure, and do the evaluation inside. So for an expression x given here, I get a lambda, and I call it within a dynamic environment, and evaluate each closure generated at compile time, generated for the sub-expression. So it compiles a source S expression into a lambda, and if you call this lambda, or a procedure value, if you call this procedure, you get the result of that expression. That's exactly. And then here you have a symbol which would be a variable if you evaluate it, and you do the same for variable access. Different cases. One case is a global value, one is a lexical, and you have a compile time environment. This is empty at the beginning, and for every variable binding introduced, you extend this environment. So we have actually two environments here. One, while translating this expression, this is the compile time environment where you map names, variable names to an index, and you have a runtime environment. This is actually the argument to the procedure this function returns. And at runtime, you pick out the values of this runtime environment. So this environment here in if we see it, it's threaded through the execution of the sub-expressions. This is a v, and they give it to this sub-expression, this sub-expression, and so it's basically very simple. You just have to map variables to locations inside this environment, and there's no magic involved. It's just that. There are specific functions here that I haven't implemented here, but it's the how you store this compile time environment it doesn't matter. You can use a big list or a vector or something. It's just you build up the locations, and which you use at runtime to extract the actual values. Okay, this is confusing. I know it's very simple, really, but it sounds more confusing, especially how I explain it. Okay, now we get to the interesting part, the compilation part. Now this is what I know more about, so we hope this gets a bit more better to understand. Okay, compiling, of course, for high, theoretically maximum speed, depending on millions of factors. There are two ways, there are two approaches. Ahead of time, AOT, which means you compile it before you execute it, or just in time, you generate the code on the fly, compile it during execution, like Java implementations do that, and Yeah, these are the basic strategies. Now, compile to what? That's now the big question. One way is to compile to machine code. That's obvious for maximum performance. There are many schemes that do that. MIT scheme, J scheme, Larceny is a very good implementation. Icarus is very good and very fast too. This is in theory the most performance, the fastest approach to get most performance. It's very complex. You have to know a lot about CPU architecture and its performance characteristics, which is very hard on modern CPUs. Instruction pairing, pipelines, all this stuff, this black magic nobody knows about. You have to know about this to get raw machine code fast. And all the knowledge that's stored inside a GCC backend or LLVM or so, you have to have yourself. It's very work intensive, and for every target platform, for every processor architecture you're generating code for, you have to write a backend. This can be abstracted up to a certain level, but you have to know all the nitty-gritty details about x86 and ARM, at least, if you want to be useful to anybody. All right. The other way is use an existing backend. Use a backend of an existing compiler. There's GCC, for example. You can write a GCC. One could write a GCC front end. Nobody does this, of course, because the code is so horrible, but it's possible. Nobody did this so far, which kind of points into that direction. LLVM is the obvious choice for writing a backend. You have a big runtime dependency there, which might be a problem. There are other code generation libraries like New Lightning. I don't know. It's very old. It's not maintained anymore officially, I think. LibJit, there are probably loads more. These libraries give you an API to put together pieces of machine code, and this is another option. Now this is kind of slipped in. Tracing compilers. This is just a different approach. It's used in JavaScript engines, among others. What you do there is you analyze the control flow during interpretation and record information. You record the heads or the starts of loops, and then you identify hot regions in the code, like a classical JIT compiler, but you record actual information about the executed of the interpreted code, like type information, for example, what variables had which type and so on. And then if you see this loop is repeated and you have recorded information, you can generate optimized code for this particular set of types, and whatever is inferred or whatever is recorded during interpretation. As I said, JavaScript engines, I think Spider Monkey or Jaeger Monkey, that's I think the newest one. They use this approach. Lua, the scripting language, there's a JIT compiler that uses this approach. It's supposed to be extremely fast. It's supposed to be actually in one benchmark on the language shootout. It's supposed to beat Fortran in some numerical benchmarks. This has to be taken with a grain of salt, of course. It's benchmarks is a subject by itself. This can be very fast. It depends on the execution pattern of the code, but it's also highly complex. These are very complex engines that it's a lot of effort to implement that. Okay. Another approach to, or another alternative to generating native code or raw machine code is, of course, compiled to C or C++ or Objective-C. This is straightforward. I mean, it's the basics are easy to do. You have functions, you have values, variables, pointers, everything. It gets complicated when you get to the details, but it's an obvious choice. We can take advantage of the optimizations done by the C compiler. This also depends on how you generate the code, but as I said before, the specific knowledge, the black magic you have to know about the target platform, it's all in there. People have put decades of work into it. Tail calls and continuations are getting difficult. If you compile to C, you will have to think about how to implement these language features, because C doesn't have tail calls. It has tail calls in certain situations, but that's compiler specific and specific on a few other factors. And continuations are of course not there. You have extra overhead. The compile time to run the C compiler is of course not zero, but it's getting faster on modern desktop machines. It's not that terrible. It can actually be done interactively. There's a Lisp implementation, GUI. It's dead, but it has. What they did, every interactive expression entered at the read eval print loop was actually compiled by the C compiler into a shared library, loaded, executed, and so it works. You don't even notice, because the machine is fast enough. And if you have small snippets of code, it can be compiled very fast. Okay. This is another way, of course, you compile to Java code, either source or bytecode, Java bytecode in class files. Kawa and Bigloo have, Kawa is a Java-based scheme implementation. Bigloo has, among other backends, has a Java backend. You have a large runtime system, of course. You have garbage collection. Some things get tricky. You have, for example, boxing. That means if you have a generic function call or procedure call mechanism, like apply, you have to pass objects of unknown type to a procedure. So you need to box every immediate value, like integers and so on. This has a certain overhead. Another problem is that bytecode verification can fail if you generate bytecode on the fly, for example, or you generate bytecode yourself. You are not treating the paths of the Java C compiler, and this can expose corner cases during bytecode verification at runtime, or shortly before runtime. And if you generate bytecode at runtime, quasi evaluating, but compiling to bytecode. There are libraries for compiling to bytecode. This won't work on specific or custom JVMs or Dalvik, which the Android JVM, which is not a JVM, but it executes Java. This won't work. So this is a bit difficult. You have to compile it ahead of time. And you have the startup overhead of Java, of course. A JVM needs to be started and loaded, and this overhead is not negligible. Another target language, JavaScript, for example. It's used more and more. Hop is a cool scheme implementation that's based on Bigloo compiler. Compiles to JavaScript, can be executed in web pages. Spock is another one. And you have all the web stuff. You can embed sophisticated programs written in Scheme into a web page. JavaScript is very flexible. It's a very nice target language, and the engines are getting better and better. They are like a said earlier, these tracing compilers are very, very good, and the engines are getting faster by the year, and so the overhead isn't that high anymore. JavaScript actually has become a processor architecture, more or less. It has evolved from the stepchild of the scripting language world into a CPU. You can actually take C and compile it to JavaScript using inscription, and it's just a matter of time when Linux will run in a browser, and it already does, I think. Yeah. Oops, sorry, I missed. So, okay. Another option, compiled to your common Lisp, done in Rabbit. Rabbit was the first scheme compiler ever. It was kind of a prototype implementation. Common Lisp has a big runtime system, very rich, very many loads of libraries and loads of language facilities that you can use. You don't have tail calls, or not necessarily. Most implementations have tail calls, but they're not in the standard, so you cannot rely on them. You don't have continuations. But I mean, if you go that far, you might as well code in Common Lisp or use pseudo-scheme, which is a scheme implementation embedded in Common Lisp. It's an option if you just want to play and try it out. Okay, and finally, you can of course compile to every known language: Erlang, Haskell, Objective-Camel. People are doing that, having a Lisp syntax and generate this code in these languages. And why not? There are many interesting options to try out. And finally, people are compiling actually to hardware. There's a scheme implementation called shard, which generates FPGA, or it generates a Verilog or VHDL code, and you can actually compile to matter. Yeah, and this is crazy and it's cool, but it's also a very, very restricted scheme. I'll talk about this later. Okay. Compiling to C, I'm going to concentrate on this subject because that's what we did for Chicken, and going into a bit more detail here. Direct C generation means just take the code, the basic control flow, compile it into C. Don't worry too much about tail calls and continuation implementation, and there are a few implementations that do that. That scheme to C was the first scheme compiler that generated C. Bigloo, Stalin. Yeah, I'm going to talk about this later. It's great, and these just take this code and compile it into more or less idiomatic C. You have to make compromises. If you do this direct approach, tail calls are not generally available, or you have to be very, very careful about the code, the generated code, so that, for example, GCC's tail call or sibling call optimization, I think they call it, before that catches. You cannot take the address of local variables and all sorts of stuff. Is not allowed. There are no download continuations. There are continuations in one direction, so you can use them practically to implement exceptions. Full continuations, where you can actually return from a function twice, are not possible if you directly compile into C. Or with a very high overhead, which slows down all code, not only the code that is continuation intensive. And the third the last option to get around these limitations is to have very, very sophisticated flow analysis and static analysis, which is done by Stalin, and this is very, very difficult. These are there were certain strategies now how to get around these limitations, how to have these features, continuations and tail calls. One is the big switch. The next is trampolines and chaining on the MTA. I'm going to talk about these three now in turn. The big switch, you generate a big switch statement where each case represents a piece of code, a procedure, and you use goto. You actually have goto then in this single switch, in the function, single procedure. This is important, and you can implement arbitrary control flow. An alternative to goto is just a loop, looping around the switch and just set a variable. But it's basically doing the same thing. The compiler is probably generating the same code anyway. But this is one way to implement tail calls. GCC has some extensions. Now, GCC extensions are, as we all know, quasi-standard. So most LLVM or Clang or so, they have these extensions too. Computed goto, where you can actually take an arbitrary pointer and jump to it. Is available, and this can make this very fast, and can be used to implement indirect jumps and all this stuff. The disadvantage is you generate a very large function. There's actually one C function for your whole program, and this can get obviously very, very large. And the larger the function, the longer are the compile times. This is extreme. If you have the compile time of a C program largely depends on the size of the functions, not the code together, or the whole body of code. But the bigger the function is, the more optimizations have to be done, and it gets more complicated. Of course. The next alternative is trampolines. Showing an example in a moment. You generate functions that return a pointer to the next function to be called. So you can actually have this iteration that tail recursion makes possible by always having a loop doing jumps. And you have, this is what I mean, the driver loop. This is the term for it. This is an example from the paper by David Tarditi, who invented this. This is standard ML. I'm cheating here. This is a Lisp talk, but it's simple enough to be left as it is. You have a function with two local functions. You call this the first local function. This calls again the other local function, and this goes about chuck. It goes ping pong, and they call each other up to a certain limit and then return. And these calls are all in tail position. So bar calls baz in tail position. This calls bar again, and so until the argument is 0, and then it returns a stupid string in this case. But this is now heavily tail recursive. The calls are in tail position. This is after a few transformations. Actually, this looks like continuation parsing style. We'll come to this later. And what you do is you simplify the program here. Those pattern matching parts are transformed into conditionals, and you have explicit continuations. You have an explicit thing that represents the return point. And now, when I talk about CPS, this is a bit more obvious. But now here's this driver loop, while one, and you have a label sort of, and you call this function, and this function again returns a new function, and this is called again. So you have an iteration. No stack is building up. If the last thing a function is doing here now, bar and bus, these are they represent this. When it returns, when the edge case or the final condition holds, it sets a return value, and if it calls the other function, it just returns it. So this goes back here. It's a result of this loop, and the loop is re-entered again, and the function is called again. So no stack is building up. It's iterative. You have this loop can run for hours, run forever, and this is one way to implement tail calls. It all kinds of interdepends. So we have to talk about continuation parsing style to make this more clear. Sorry. Oh God. Yeah. And the third option, trampolines, a big switch, trampolines, the third option to implement these features, tail call CPS basically, is called chaining on the MTA. It's by Henry Baker, who invented this. This is the approach used in chicken. And actually chicken only, I think, really. Funnily enough, because it's a nice strategy. What you do is you convert to continuation parsing style. I give an example in a moment. And you translate this continuation parsing style to C. You allocate everything on the stack, and you just call functions in tail position, and just don't forget about the stack. Let it grow, and look what happens. Of course, you check after a while. And then when call frames have built up, you pull out all the information from the call frames that you need, make a long jump or an exception or return, and start again. So you have again a driver loop, but not inside a single function, but on the call stack. And you build it up and jump back, and so on. And as long as you extract the live data, the interesting information out of the stack frames, it works. And everything that you're not extracting there is dead data, is unused data. We see it here. This is a code example. This is getting even messier now. I hope someone can read it. This is from the paper it's not by me actually. So it's not completely my fault. It's from Henry Baker's paper. This is the URL. You have a function. Gets an environment continuation. You have an explicit continuation argument that represents where this function is returning to. And you take the address of a local variable. You check whether a stack limit is reached. You create an object that holds all the information that's locally available. That's the environment, the continuation, arguments of this function, and store it in the closure. And then you do a garbage collection, starting from this closure, which is the root, and then return to the bottom. At the bottom, there's a kind of a loop that picks out this information and starts again. This is another function here that this is done. Doesn't really clear up. We have to come to continue. Oh God. To continuation parsing style. To make this more obvious. I have organized this wrong. So. What you do is you use the stack that's building up as an allocation area, and when you come to the top, when you have call frames have added up, you extract the data, you extract the values, and just throw everything away and go back to the bottom. That's the point. There are a few complications for if you call foreign functions and so, but it works, and it's used heavily, and it's relatively portable. That's the nice thing about it. Okay. Now this is a bit. It's a mess really, because we are jumping here from, but everything is intertwined. So bear with me, please. So if we're going to write a compiler now, we have to start somewhere, and the obvious place is at the front end where the syntax expansion takes place. This is the first stage of a compiler before you come to these lower level things like closures and continuations and so on. And this is the first step. This is basically macro expansion, which is one of the nice corners of Lisp and Scheme, Lisp in general and Scheme. There are two different expansion ways, or ways of defining macros, or syntax. That's the official term in Scheme. It's declarative macros versus procedural macros. Procedural macros are, you can execute arbitrary code that expands into code, and this is then the result of the expansion, and this is then compiled. We have a few examples in a moment. Declarative means you just give a pattern and a template and let the system, the macro expansion mechanism, figure out the details. Declarative means you specify the what. Procedural, you specify the how. There are some issues regarded to hygiene or referential transparency when expanding macros. You don't want to capture free identifiers. You don't want to capture. You want to expansion to work everywhere. And then you have another issue is that expansion time of syntax is not the same as execution time. So if you have a macro, like in closure, for example, and this macro needs code in the program that's using this macro, then you have a problem, because you need the code to run to actually be able to compile it, which is difficult. And so declarative macro systems get around this problem, but with procedural macro systems you have to take care of that. The simplest procedural macro facility is def macro, used in common Lisp. I think Clojure, I don't know Clojure too well to say anything about it, but I think it has this kind of macro. You have the defining form. Say we have a while loop here, and you put together with the famous quasi-quote, you put together a piece of code again that implements this loop. Loop is an identifier generated on the fly, some weird internal symbol, and you just piece by piece you put everything together, this, and start the loop. This is the code that actually executed. This is simple, straightforward. For complex macros, this can get very ugly. And the problem is, of course, in Scheme, everything can be redefined. It's very general, as I said in the beginning. Now, nobody guarantees that if means if in this context, or let is really let in this context, because the code using this while could actually redefine let and if. And this is not handled by macro style macros. This is what hygiene basically is about, hygiene in macro expansion context. Syntax rules is the standard macro system in Scheme. It is hygienic. It's a declarative way of specifying macros, and for simple things is relatively easy to use. So here we have this while macro, this loop macro again. Syntax rules means you give it a rule, a so-called pattern. That's right, it's a pattern. We ignore the first part because it's the while symbol. It has one argument that represents the condition and a body, the loop body that executes. And then you put together, and then you give the template of the code that's going to be produced for this use of the macro. And it's simple. And the system figures out that that this X and this body represent parts of the code, and this takes care of the hygiene issues. So if let is redefined around the place where this while macro is used, it will still represent the original let. Here at this time I defined this macro. That's the basic rule, really. Identifiers in syntax rules macros, identifiers have the meaning at the point of the definition of the macro, not of the use. So if I use this macro somewhere, it doesn't matter how these identifiers are redefined. The meaning of the identifiers at this point of definition is used. So you don't get conflicts, you don't have interactions. Hygienic means exactly this variable capture. If I use this while macro now, and I have let, I can do that. I can redefine let, I can redefine everything. But syntax rules, the mechanism how it's implemented, guarantees that these redefinitions don't catch in this case of the code. So it's like if I use while inside some code, it just marks them. This let really means a real let, not any let that's possibly defined here. And is this somehow sufficient? Okay. When we have, this is another one. Yeah, perhaps this explains it a bit, because this is another macro facility. It's called explicit renaming, and this does explicitly what syntax rules does behind the scenes. This is again our while macro. Blah 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 blah. Never mind. This is the form, the form representing the source code. That this use of the while, and two extra arguments: rename and compare. Two procedures. Sorry, that can be used to generate new names, new identifiers that have the meaning I intend them to have. So if I take it in this context, the context is captured here in these two procedures, and I want a variable now that represents this if symbol, but with the right meaning, of course. Let begin loop, and then it puts together the new source code form. This looks worse than it is. This is just a naming convention used in these percent signs. A naming convention used. This is basically the same, or this is a mixture. It's basically the same of the define macro style macro, but it does the renaming that syntax rules does behind the scenes. So this has the same effect as the syntax rules macro by making sure this let and this if have the meaning they had at point of definition. And this is, again, guarantees hygiene or referential transparency. Yeah. There's another way to go one step further there. It's called implicit renaming. So we are all giving all kinds of options now. I'm giving all kinds of. Implicit renaming is similar to explicit renaming, obviously, but it just turns it around. It does, as we've seen here, this looks a bit tedious, really. And if you have a complex macro, you have loads of identifiers that you have to generate and rename, and this gets very ugly. So the obvious thing to do is just let's turn it around. Just rename by default, and just mark those identifiers that we specifically want to capture, which we don't want to be hygienic, which is called injection. This is again the loop. You're probably sick of it now, but I'm still using it because it makes it a bit more clear. And what this, I give it the normal code, and just the renaming is done automatically. It's obvious, but nobody came upon it. But he did. Peter, for chicken, he has implemented it. There's a paper by, I think, what's his name? Kohlstetter. Kohlstetter, wasn't it that the guy? Never mind. Huh? Kohlbeck, that's right. This is, the original paper about hygienic macros 200 years ago. And he kind of hints at this, I think. And this is very nice because it's you have the best of both worlds. You have basically the same thing as in define macro, but the system or the mechanism takes care of the renaming part. We have an example here with injection now, which shows this specific case of breaking hygiene. And it's very nice, getting more and more fashionable among chicken schemas because it's so easy to use. And, thank you, Peter. Here we have an example of a case where we inject an identifier. It's again the while macro. Again we have the form, and we have these two special arguments, procedures. We take apart the source expression, test, body, and now we generate an identifier and inject it into the context of the use of the macro. I hope this is correct what I'm telling now, because I'm very conservative. I use syntax rules most, and so this is a slight variant now. This is a while with an extension that's called exit. So inside this loop, you can call a procedure named exit, and this will exit the loop. This is called with current continuation. So here we have a variable that represents a function, a procedure that leaves this context, this execution context. And we want this to be available in the code. But to do this, we have to break hygiene. We want to introduce an implicit name, and inject does this. It's actually the other way around. It breaks hygiene to say, okay, every use of exit of the symbol exit here, every use of exit has a special meaning, and this is basically the intention of it. Because there are some cases when you want to do this, you want to have an implicit meaning of an identifier. Yeah, otherwise it's just a normal loop. Here, everything is renamed automatically by this IR macro transformer thing, by the implicit renaming facility, and you just specify the cases where you don't want this to be done. And you can build relatively complex macros and still have the basic work just with S expressions and don't have to worry about renaming and everything. Okay. This is another facility, syntactic closures. It's a bit older than this. I don't know too much about it, so what you do is the closing of a lexical environment that you do with environments and variables, and you do with at runtime, you can extend this to syntax, because that's exactly the point when I say differentiate between the time of use and the time of definition of a macro. You close over the point over the syntactic meaning of an identifier, like let, and here we have this loop again. This is a different loop now. It doesn't matter really. We have again the same case now that exit has an implicit meaning, and what we do here is we take this identifier named exit, or actually a whole form, and say capture the meaning. Now we capture the meaning of of this. I think there's a mistake in there. It is correct. Do you know? No, it does automatic renaming, but it captures the meaning of the exit here inside this macro. So this is actually a complete mess. Never mind. Okay. Syntax case is, nobody uses syntactic closures anyway, so let's just continue. Syntax case is, it was standardized in R6RS. It's very powerful, used in many implementations, Racket and among others. And it's the big iron of macro expander systems. Not everybody likes it, but it's very powerful. That's no doubt about it. What you do is you actually treat the source code as an abstract syntax tree, and you have a special API to access the parts, the pieces of the source expression, and extract the symbols and lists and work with them and guarantee renaming and everything. So here we have our famous while loop again. This is syntax case. This is a pattern matching facility. Takes a source expression, picks out the parts of it, and here we now have more complex forms that generate identifiers inside a certain context, and puts together a new form. This is a form, takes care of renaming, takes care of hygiene and everything. And this is very, very, very powerful, very clean. It's also very explicit. And it's getting complicated because we really have a special API to work with syntax objects. These are not source expressions like in usual list macros. These are abstract data types containing, among other information, the source expressions. The good thing about it is you can store extra information, line numbers, source files, whatever. In Racket, for example, the Racket implementation, they have all sorts of extra fancy stuff for their development environment, where you can you can jump to the place where the macro is defined and where it's used and everything. So we have lots of context information, which is very nice for debugging, for making the expansion more transparent. But it's not, it's icky really. I mean, you're not working with S expressions. It's not very nice. That's my personal opinion. So it depends on the culture. In Racket and in Shea scheme, Larceny, Icarus, they're using it heavily. The chicken world doesn't use it that much because it's not available, of course, and because but nobody really asks about it. It's implicit renaming, explicit renaming. It all works, or syntax rules, which has another advantage that it's standard. Okay, there are a few portable macro expanders that you can use if you want to play with this or implement an interpreter or compiler. There's LExpander, my personal favorite. It's a syntax rules expander. It's with a few very cool extensions. Not too big, easy to use. Weird code, but it's very powerful and it's very general. It takes syntax rules and generalizes it. Then there's André van Tonder. This is a guy from Belgium, I think. He wrote an expander, kind of a reference implementation for the R6RS module system and macro expansion system. Very powerful. And then there's P syntax used in Shea scheme, and there's a free package of the macro expander that provides syntax case and I think a module facility too. If you have modules and hygienic macros, it has to work together anyway. So I think André van Tonder's expander actually handles separate compilation, which is an issue with macro packages. You really have to look at the stuff to get at the details, because there are various options to get hooked into an implementation. But they have these hooks, so it's very nice that people are actually writing this and putting this on the net, and you can just take them and pipe your code through it and have all the syntax stuff worked out. Okay, now we get back on track to compilation, which comes after the syntax expansion, and then we get to the CPS part. Yeah, for compilation we need an intermediate representation of our code, and we can actually use scheme. I mean, it's a data structure. It's S expressions. Performing transformations on the code is straightforward. It's like everybody does this in macros, so why not in a compiler? And you can actually run your intermediate representation. It's executable code. If you have macros that implement the specific parts, you can actually run your different stages of the code compiled by produced by different stages of the compiler. And this is a very nice feature. You don't have to do this, but you can, and this is quite nice. Again, direct style, I talked about this earlier. Then there is continuation passing style, which is another strategy of compiling. And there's ANF, which does serialization. What CPS does, CPS is the older approach. It makes continuations explicit, and it serializes the code. If you have a nested function call or procedure call or something, you want to have it taken apart. First this argument, first the next argument, and then I want to do the call. ANF is an algorithm that does this serialization part without the continuations. There's a nice paper about this that's worth reading. Something is messed up here. Okay. Is this correct? Yeah. I think somehow the slides slipped. Yeah, again, CPS it's creeping up everywhere. For implementing continuations, there are various approaches. You can do stack snapshots. You can, which is a kind of brute force approach. There are certain, I think this is Linux specific ways of getting at the execution context, specifically the stack. There's an approach called stack reconstruction that also can be used to implement continuations. And there's again CPS conversion. We have details about this later. Stack reconstruction, never mind that. Okay. CPS conversion. Now I'm talking about CPS conversion all the time, and we need an example badly. What it does is it creates something that represents this continuation, and we pay a slight cost for procedure calls, but the continuations itself, once we did this transformation, which it is a code transformation, we get very fast or nearly free continuations, which is important if you're doing coroutines or multi-thread or green threads, user level threads, which can be implemented using them, where performance is really important. Okay, now we have an example. Now finally we get to find out what it is. This is a stupid, silly function. I don't have to explain it. The faculty function and calls it. And this is now the CPS conversion of this function. And what does this mean? Explicit continuations. It takes the function FAC and transforms it into this. We add an explicit argument to every function we have and to every function call. So here we call 0, the 0 procedure. It usually takes one argument. We add another argument, which is a function, a procedure again, that does whatever comes after the call. So after the call to 0, we check what the result is and do different things depending on the result. And now, this is what we do now. We call 0 with a procedure that does this, checks the result and do something else. What this transformation does is we turn everything around, and we have in every function, every procedure call ends up being in tail position. So this is the first, the normal argument. It's underwent renaming here, so never mind the 44 at the end. And we call the function, give it a closure that represents the rest of whatever comes now, do the test, and this is the actual return. The return from this faculty function is now converted into a call to the continuation with the result. And again, in the other part, here we have another call. We are not returning, we are calling minus, and we give it a continuation that does what comes after the minus, the call to minus, which is calling FAC again. And after FAC, we call times or star with another continuation, and so on. And every call now here, FAC minus 0, is in tail position. So it can be jump. It just doesn't matter. Or in the Cheney on the MTA approach we had earlier, you just call, and then you just jump back to the bottom. And you have the continuation here. And it's, once this transformation, you have the extra argument. This is an extra runtime cost, but these continuations are there. They are explicit, and they have however you use them, there's no penalty involved. This this stuff around here is just what this define expands into. It defines a local procedure, sets the variable to the value of it. Yeah, and this is the first call here with a continuation argument, and this continuation argument does again what comes after the call and the original argument. I hope this is somehow makes a bit of sense, but it's a straightforward transformation really, and it's used in a few languages. It's not used in Scheme that much, or in Lisp, because it came out of fashion at a certain time. Oops, no. Okay. And this CPS transformation now is fundamental, because it's everything has to be transformed in this way, and especially if calling into foreign functions or something, you have to, if you call foreign code like C code or Java code, depending on the compiler, you have to keep that in mind. Okay. Now, if we have continuations, we need something to, after we have that, we need something to represent closures, procedures, together with the static environment. Because a closure in a functional language is not only the code, it's also the free variables, the context where this function, this procedure is used. And there are different approaches to implement that. One approach is linked environments, and we have so-called display closures and flat closures. Linked environments is the obvious approach. You have just every variable environment you introduce for arguments or for let-bound variables. It's just a vector or something, and you link them together. So here we have a silly, stupid, completely contrived example function. It has a local function here with two arguments, and it returns another function to make it even more contrived, which then uses these variables. These are called now free variables because they are free in this lambda here. B, X, and Y are not defined in there. They are captured. They are defined outside, and when this lambda is returned from lowrider and again here used, these variables don't exist. They do exist, but they are not there anymore. They are captured inside this procedure. I've tried to give a more or less not graphic enough, a description of this. So if I call this function brick house with two arguments, which returns a function for one argument, I get something that a procedure that is a piece of code, actually this here, and the environment. And the environment, the static environment, the environment at the time of the capture. You see the analogy to the syntax stuff a bit, I hope, perhaps. And E1 is the environment captured, and it contains X and Y. This is this. And a link to the next outer environment. This is E2, and this contains A and B. And so this is what's meant with linked environments. They are linked together, and so if you just pick out the values, then if you compile this into whatever you want to compile it to, you pick out the variable values out of these environments. This handles sharing and everything. So this is a natural approach to implement environments. An optimization of that is display closures. That means that every environment is just a vector or a sequence of values, and your closure that you return just takes all these single environments and adds them to the closure. You don't have a single environment, but you have these displays. That's where the term comes from. You have one for the outer function, a and b. You have one for the inner function, x and y. And so if, say, the second here, x and y, wouldn't be used, then we could just leave that out. Or you just pick out these frames, these environments that you want. It's just an optimization to reduce the amount of storage needed at runtime in the linked environment, not in the procedure. The procedure grows. And the obvious continuing that to the obvious solution is to have flat closures, that you actually store the values of those free variables in the closure. Here we have it. The code. These are b, x, and y are the free variables used in this procedure. And we just store the values in there. That's it. We just take the free variables, put them in there. There's an extra catch if you have an assignment and the variable is used in different contexts. You have to introduce an indirection. We have an example of that later. And this is you don't have any environment, any linked chain of environments hanging around at runtime. You don't need them, and it has a few advantages. Procedures with loads of free variables can get pretty large, but still you don't have to maintain something at a runtime. And local variables like this Q, for example, they don't have to be handled specifically at all. They can be put in registers when you compile it to C or machine code. And this is very fast, of course. If you have one of these approaches here, the variables are stored in some explicit runtime data structure, and you need an extra indirection, and there's no chance a C compiler, for example, makes to improve it. So this is a nice approach, and that's used in many implementations and in Chicken actually too. Okay, now I talked about closures a lot. How to implement these closures now. You need a transformation for doing this flat, for these God, this is another terrible example here. Never mind that. Talking about CPS and flat closures, it has one nice example, not one nice advantage. It's some weird term called save for space complexity. It's by Andrew Appel, who invented or who gave this a name. Doing all this crazy transformations and taking care of only storing globally environments and free variables, so is done to reduce the amount of data hanging around at runtime. If you have these linked environments I talked about earlier, and there are pointers to big data structures in these environments, then they cannot be garbage collected. They are just hanging around there until the environment is thrown away because the function returns. And if we do this CPS transformation and flat closures, we have the nice property that the data or the free variables that are not in use anymore can be can be garbage collected. So if we have this function now, this is a very simple example, gets a huge data structure, And now we call this procedure with this data structure. And then next, we don't need this data structure anymore. At this point here, this point, this can be collected. Now, if you take this procedure and compile it mentally into C, you would see, of course, data is some local variable. It's still alive. It's still alive until the function returns. But in this representation, at the point where we have this CPS conversion, at the point this is called, there is no use of this variable anymore. And here we see this. This is T2. T2 is this flashlight procedure. Here is it called. We have a CPS conversion done. This is the continuation. It's slightly transformed now. And you see this data 44 now. It's given to Superfly as an argument. We have a explicit continuation. And this is the rest. There's nothing coming after it. This is CPS. Here is this function called, but data is gone. Data is not used anymore. The rest of the computation, which is what continuation parsing style is all about, has no reference to this variable anymore. So it can be garbage collected. So you retain data only up to the point of the last use, exactly of the last use. This is seldom really important, but when it is important, it's very, very important, because you can run out of data, and that's you run out of space, run out of memory, and this is a problem in a traditional approach that doesn't use CPS. Yeah, flat closures. I talked about this indirection with assignment. Closures, or if you have lexical variables here, like this X, and it's used inside here. It's a free variable inside this procedure, but it's also used here. It's shared. It's changes to the variable at one place have to be reflected at the other use of the variable. And if we have this flat closure conversion and just put the value in there, we have to handle the case that someone is modifying the variable destructively from the outside. And here we have it again. I have spared you the CPS conversion here because I just want to show you the example. This is a variable X. It's a free variable and packed in the closure here. Never mind this. And what we do is we create a box around it, a vector, one element vector that just holds the value, and every assignment is transformed into an indirect destructive modification of this box. So if the flat closure doesn't hold the value itself, but the box containing the value, then we can modify it. It's the well-known thing. Every programming problem can be solved with an extra indirection, and this is one use of it. Now another detail about this. Okay, now we get to the really interesting part. I hope you're still with me, you didn't fall asleep yet. So we have the interesting optimizations done. The most important of them being inlining, which means replacing a procedure call with the actual code of the procedure. It's obvious, of course. Reduces the overhead to 0, hopefully, and what is important, if you have intrinsic operations, fundamental operations like adding small integers or so, you don't want to call into a runtime system. You want to have it directly in the code you generate. So this is the most important optimization. And a lot of that follows from that. specifically for primitive procedures. That is the standard procedures available in Scheme. Because in Scheme, every global variable can be redefined. Plus doesn't have to be plus. You can say set plus minus. It's completely legal. The only thing the standard guarantees is that the standard procedures work. So, but you can redefine everything lexically and or locally and globally. So, but if you compile code that uses plus a lot, you want it to be fast, and you want to use the minimal. You want to have minimal overhead. Oops. And until you have handled this case of somehow getting at the basic of the original meaning of an identifier, all optimizations are useless, because this is the highest cost, and this is the most expensive cost of Scheme, which has to be solved. And what you can do is you can use a flow analysis. Okay, you can analyze the program and look, okay, this is plus there and it's redefined there or not, and you know what type it is, but this is very complicated. Or you use a module system. You have some system that maps identifiers to meaning. Or you can just cheat. We do this in Chicken, actually. And it's okay, because we just say, okay, in the default compilation mode, we say plus means plus. If you redefine it, it's your own fault. You can switch that off, of course, but in practice, it's not done that much. And if you are really doing that, then you will have your reasons, and you can switch the optimization off. And of course, doing something like this, eval read, breaks everything. So you need some way to handle this. Okay, then what you have, the usual optimization stuff, CSE, common sub-expression elimination, constant folding, variable propagation, that's it. The usual stuff done in compilers. I'm not going to talk about these. You can do them, but they're not as important as the inlining part is. Lambda lifting is another approach where you actually lift local procedures by these free variables, which we had with closures and environments and so on. They're given as explicit parameters. No, I'm going to leave this. And the next thing is getting a type information, because now you have the primitive procedures. You have some way you have chosen some way to guarantee they do what you want. You guarantee the redefinition problem. Next is you need access to the types. You want this code to be fast, so you have to find a way to get a type information for variables as much as possible. You can ignore it, but if you have it, you can try to squeeze out more performance. There are basically two approaches to this type analysis. One is Hindley-Milner, which is used in static languages like StandardML and Haskell, for example. It's where a variable has a type. You infer, you have some code, and you infer the type of a variable according to its uses. The other one is flow analysis. That means actually executing the code at compile time up to a certain limit, but you take time also into account. This is much more powerful, but it's more complex, and it has limitations, because the meaning of a variable is only you can only get at it if you're really analyzing everything. If you have just one big program and you do a complete analysis, the complete static analysis of the whole program, which is, of course, a difficult thing to do. There's no way dynamic code can be executed dynamically, loaded dynamically, and no eval, for example. But this gives most information. There are a few compilers that do these type analysis. There's Schlep from the guy who implemented SCM. It's very, very basic, very simple, and it actually associates variable names with types, like good old BASIC and Fortran, and so. It works for simple cases, simple driver programming in Linux using a scheme syntax. Pre-scheme is another scheme or sort of scheme system. It's used in scheme 48, which has a Hindley-Milner type inference. It's actually used to implement a bytecode interpreter in scheme, used as the implementation for another scheme. It's very elegant. So this is a low-level scheme that is just used to implement the engine where the real scheme is running on. And they have this Hindley-Milner type inference algorithm. They are defining the bytecode interpreter in a scheme-like language. Only for the bytecode interpreter, not for the actual scheme implementation itself. Does no type analysis. It's a interpreter. That's right. It's a restriction. It's a restricted dialect for one specific use. Soft scheme. Soft scheme is nice, very old, not maintained anymore. Of course, unfortunately, it's just a front end. It's not really a full scheme system. It takes scheme source code and annotates it and introduces explicit checks, and then you can write macros for that but it's a kind of a source code, a preprocessor, really. Take a look at it. It's flying around on the net and slowly dying, but have a look. It's very basic, R4RS, I think, but it's worth looking, really. There are so many cool things dying. Bigelow does type analysis, Stalin does type analysis. Chicken does also a bit of type analysis, only for local functions, and probably many others do this to eke out more performance. I'm coming to this in a moment. There it is. It's called the scrutinizer. That's the type analysis part. Now this is the peak of contrived code, but you don't have to understand it. That's a nice part. It's just that it's intended to show how this analysis works. So we have a function. We are just talking about local analysis. We are not taking the global context into account. We have two variables and we have a function. Okay, all right, let's enter it. Now that's how this type analysis works. It's a restricted local flow analysis in Chicken, and this is a piece of code, and I'm just showing here now. I'm going to walk through this code and tell you what Chicken infers from these variables, or what types it finds out. Sort of, yeah, that's right. So we go into it now, and we assume, that's Chicken's default mode, that these standard functions, cons, plus, vector, p, and so on, have their obvious meaning. They're not redefined. It's a default compilation mode. If you have a module system, then you can make this sure in a cleaner way. We assume this is the case now, and Chicken, the compiler, assumes it too, because it's going to replace this with an intrinsic. So what do we know now? We walk through the code. We first bind Z. Now we have a plus procedure. The plus procedure is well known to accept numeric arguments. So x must obviously be a number, because if plus returns, x was a number. Otherwise, it would have thrown an error. So we know x is a number at this point. Now we go on. Z must be a number too, because the result of plus is known to be, is globally known. There's a global big table of type definitions for these standard procedures. So we know now Z and X must be numbers. Next comes the next part. Cons, here's the same. If cons returns, then we know X, we know that, never mind. If cons returns, now we have U is known to be a pair. Cons returns a pair. So we know actually the types of 3 variables already. And this is how it actually continues. The next interesting part is, here we have a conditional, and we have a predicate in the conditional part, in the test part of the conditional. We know now, or chicken scrutinizer knows, that if this code is executed, the predicate must have returned true. So epsilon, y actually must be a vector. So we know now y is a vector. Okay, and it continues this way. Just walk the code and look at where the variables are used, in what place of these procedures, and you figure out more and more type information. And we know U is a pair now. This is a type the representation of the type. It's a pair with car and CUDA types, which are wildcards. We don't know them yet. And we call a function, and now we set a variable. Now this is a point that makes everything more complicated. That's assignment, destructive assignment. It might change the type of a variable. Z now changes its type. We know string append returns a string always. It always returns a string. So we know Z is a string, and so on. And now here, this is the result of this part of the conditional must be a char, and so on. So Q is a char here, as a character type. Here's another special case. We know that error does not return. Error just blows up. So we know that any information, any type information inferred here in this case, say something else comes after that, we know that this at this point where Q executes, where tighten it up executes and Q has a value and is returned, we know this part of the conditional must have been true, otherwise you wouldn't have returned, otherwise error would have been called. So this gives us more type information, and it continues like that. It's still limited. But it gives, in certain places, it gives you a basic idea that we know now. Okay, here we know y is a vector because this predicate was triggered. This could never have been executed, otherwise it would not return. So we know y must be a vector. Now we can replace this vector ref with an intrinsic operation that's really fast because it knows it is a vector. I don't have to check at runtime for that. That's basically the whole point of optimization, is to get rid of everything that could possibly slow down the code and still catches errors. The errors that the standard requires to be detected, and the errors that the implementation guarantees to be detected, just to make life a little bit easier for the user of the language. There are thousands of thousands is a bit exaggerated. There are a few cases where you have to take care, because destructive modification of data is always kicking you really because so say we have construct a pair with variables of known type. We know x is a number. So here we have u must be a pair with a number as the first part, as the car of the pair. But here we call a function with u as an argument. And this function may destructively modify the pair. So after this is executed, u is not guaranteed to have a number in the car part of the pair. And these are the little complications that crop up, and users find them, and implementers have to fix them. Sorry, I can't. I know u is a pair here because const is here, because u cannot be modified outside of this scope. U is a variable in this scope, and you can pass. You are not passing the variable to this procedure. You are passing the value of the variable. The variable itself cannot change. Okay, it can change, but that's magic now. That's runtime magic where you can mutate values and so on. But the variable itself cannot be modified outside of the scope where the variable is defined. You can destructively modify only the values. Yeah. It's complicated. It's really complicated. And it's just a simple type analysis. And already finds a lot. And the funny thing is, because Dirk, you talked about optimizations. The interesting part is the optimizations aren't really that great we're doing. The nice thing is this catches errors. This catches loads of errors, because you actually know now if, say here now, we know that y is known to be a vector of numbers, and we pass it here to string append, and the compiler will give out a warning. Here, look, you are passing an argument of the wrong type to this procedure, and this catches many errors. So it turned out, it was started as an optimization, but it turned out to be actually more useful for catching user errors. And it's a nice moment when the compiler warns you about something and you think, oh boy, I didn't see that. And the compiler figured it out. Yeah.
It allows you to bubble the type checks outwards from the output string. So you can like specialize vector rest in the last line.
This one?
So that it doesn't do the type check for y there, but it can do it.
That's right. That's right.
But it can do it at the beginning of think about it instead.
It has to do it, because at the point think about it is called. It's not. Wait. At this point, it doesn't. At this point, I think I know what you're meaning. Yeah. If you pass something, if you pass something in that's not a vector, then sorry. Exactly. It won't reach this part. No, this type information is always local. It doesn't. I'm not sure I understand what you mean with bubble out, but it's a sequential. It's a sequential pass through the code. When I've analyzed this part and I reach this point, this is not going to change anymore. It's just one pass through the code. So, but if you mean that it propagates this type information, then you are right, because every use afterwards can say we do another vector f, then and of course we know that it's a vector, but it's just a local flow through the execution. Yeah.
This code wouldn't return, but all the next continuation. This goes past.
That's right.
Could you like fork off the implementation of the continuation? You know, the return value is a vector.
Yeah.
You know that
The point is, I think the point is that this whole stuff about CPS conversion and tail call optimization, it's transparent. The meaning is still the same as a normal direct representation of the code, and this analysis is actually done before the CPS transformation in Chicken, because CPS transformation, you create loads of explicit procedures. All these lambdas introduced as the continuation argument, which makes flow analysis very hard. So, because you have to track procedure values and things. So this analysis is done before the CPS conversion, because otherwise nobody would understand it. And so at least it's walking the control flow is more obvious. It's still hellishly complicated, and Chicken does a simple analysis, simple type analysis. The one who does the real type analysis, that's Stalin. Stalin is another dying project. Stalin is called Stalin because it's a static language implementation, and Stalin brutally optimizes, aggressively optimizes. And it's probably one of the smartest dynamic language compilers in the world. It's R4RS with loads of restrictions, but interestingly few restrictions, because it has so incredible analysis. It has very long compile times. A friend of mine had a 50,000 line natural language compiler, natural language translation, parsing, semantics, blah blah thingy, and he stopped the compile after a week. He killed the process. It was just too. So Stalin is incredibly slow, but it's because it really goes. It's a whole program compiler. You don't have separate modules or anything. It takes the whole world and thinks about it very long, and figures out a mass of information. All these type stuff which we amateurishly implemented for Chicken, this does the real stuff, but you pay for it in terms of waiting. The other point is that you need a lot of experience to use it, because it sometimes gives you error messages like this. This doesn't help a lot. This is a piece from the source code. It's used quite heavily in the code there. It's an interesting piece. So it has loads of options, and these options are very, very sophisticated to influence the type analysis, the flow analysis, and then you sit there and look at the man page and think, God, what does he mean with split even if not widening, or whatever. You have to know the compiler really well to use it, to learn how the compiler works, and it's a problem really, and it's not actively developed, and it's kind of getting behind. It's lagging behind in features. It doesn't even have macros. A Lisp without macros. Can you imagine that? It's and it's a pity, because it's cool, but it has some bugs, and the maintainer has stopped maintaining it, and nobody is taking over. I thought about taking it over, but I looked at the source code and it was just, this shouldn't happen. This is another thing that's related to this type analysis stuff, is unboxing. Stalin does it, of course. That means basically that you you don't have a box representation of a floating point number. It's not some scheme data structure containing a C double or something, and you work on. You want to extract the value and do the operations directly on the values themselves. Put them in local variables and registers. Do direct floating point operations. If you want to do number crunching, this is number crunching. If you want to do number crunching, you need that. If you want to approach the performance of C or Fortran, then you need that. Gambit, Bigelow, and Racket do that more or less. Chicken did have a pass for that. It was broken, of course, and it was thrown out. It will be re-implemented again because the basic optimization is not that hard, and we do the type analysis anyway. Here's an example. It's very it's from a real world example, so it's very approachable in its appearance. This is from an FFT computation. FFT computation from Brad Lucier. Brad, you see, is a math professor who's using Gambit. This is real code written by a human being. These are intrinsic operations. Here we have type-specific operations for these maths operators. Floating point times, floating points plus, minus, and so on. This is exactly for handling the case that this may mean everything. So we have specific operations to do to these type-specific arithmetic things. Loads of variables, and this code is written in a very performance-sensitive style. It's optimal, nearly. Okay, and this is the code that Gambit generates. Gambit generates C. This is piped through the preprocessor, and these are floating point variables. And it's practically handwritten C, and this is stupidly fast. And if you want to do number crunching, you have to end up with this, and what unboxing is really about, and what you need. The concept can be extended to unbox arbitrary data structures, but this is the basic stuff that you need. And even Racket, which is not targeted at this which is not targeted at being high performance, does this analysis. You had a question. Yeah, it looks pretty terrible. Yeah, it is. No, but it's not intended to be readable. You're not intended to look at it at all. So. Yeah, of course. I looked at it. Worse, much worse. You don't want to know, really. It's there. You have the CPS transformation in Chicken. That is even more strange or far away from the original code. If you have a time, some day in the future, we can look at it. And on the Chicken website, on the wiki, there are examples. There's someone tried to explain how the compiler works, and it gives loads of huge, ugly code examples. Okay, no. It's I think I'm speeding up now. Okay, you have suffered long enough, so let's. But this is interesting because this is simple. Speculative inlining, also invented by this Mark Feely guy from University of Montreal, the author of Gambit. So we know now he's really a whiz in this department. He's also an arrogant prick, but never mind. What you do is you check procedures and arguments at runtime. That sounds very simple. It also is. This is again an approach to handle the case that standard procedures don't necessarily have the meaning they should. What he does now is transform this into a runtime test. We just check at runtime, is this really car? Is this car really the car I want it to be? never mind the quote or these funny characters here. These are intrinsic operations. This is code generated by the compiler. This is an intermediate stage. We check if the variable car contains the value of the original procedure car, and if X is a car, if the argument here, this G5, is really a pair, then we can call the unsafe fast implementation. And if not, we call the variable and just look what happens and do all the runtime checking and throw an error if it doesn't, or if the user redefined car, it does whatever it should. And this is, it's actually a clever idea and it's very simple. The problem is that you have code bloat, and it can bloat quite heavily. Okay, so I'm not going to stretch it. This is just talking about stuff. You see, I had a lot of... Never mind. Okay, I'm going to... oh God, terrible. This is my final point. I want to call to arms, because I think implementing scheme is really the way to learn the language, and to get an idea of the language and of getting in to work with it. And to really learn it, one approach is to implement scheme and try it actually out. Sorry, yeah.
Actually, I think a lot of people do that, and this is why so little useful scheme protocols exist.
Probably.
They spent the rest of their lives implementing stuff.
Yeah, but it gave us a load of nice scheme implementations, and I understand I understand the point you're making. I think, but it's not Perl, where you just have some language monstrosity, and you have an implementation for that, and you use it. You put up your sleeves and you use it, because it comes from education, from the education part of language design, and you just you have a beautiful language. Really, it's called a diamond, not without reason, and you think about how to make it run, and that gives you a lot of people putting their time into trying to get it faster or getting it to run at all. But it also makes people think about the language and figure out extensions and figure out cool features and figure out new ways of implementing it. And that's the design space. That's the reason of existence, really, for our scheme. And if you, it's the other side of the coin, really. So, right. No, but you don't have to complete. You don't have to make a high performance standard implementation that everybody uses. That happens. It's just to look behind the code and see what happens there. It doesn't have to be complete. It doesn't have to be fast. It just has to give you an idea about it, and that's enough. Okay, I have put together. I'm really finished in a moment. I just want to point out a few papers that are really interesting. The Multics MacLisp compiler is old school Lisp compiler, a lingo. It's really recommended. Yeah, you have to read the acknowledgement section of the scheme shell manual. Once you've read it, you know why I say this. And there are the Lambda papers, the famous Lambda, the ultimate whatever. They are very interesting, and I really implore you to read them and to learn more about this, because it's a fascinating subject. Links? Never mind. You find it. You Google. A few books that are interesting, perhaps. Compiling with Continuations was actually the reason for writing Chicken. Lisp is in Small Pieces is another famous Lisp book, and talking about the implementation of Lisp. Essentials of Programming Languages is another one. Garbage collection by Jones and Linz if you want to know about garbage collection. But I didn't touch garbage collection today. Thank you. Thanks. All right.